All right, so now we are ready for some examples. And so when it comes to teaching this particular techniques right here, I have my own philosophy. I see that through my experience, I want my students, I want my viewers to be successfully, to be thorough with and to be solid with the partial fraction decomposition first before you can put the integral stuff on top of that. Okay, so in that way of how I see it, I want to design the first few examples, quite a few examples of mine from start here is going to be just to cover the how we can apply the partial fraction decomposition, okay, to break a starting expression into multiple partial fractions, and then once viewers feel that you are comfortable enough, right, and have learned enough and been experienced enough with partial fraction decomposition, then we're gonna then it's gonna lead. I'm gonna lead viewers and students of mine into doing some actual integral problems where the partial fraction decomposition is only part of the steps. Okay, and so here we are at example 1 right here. And of course, even and one more word before we really get started, but there will never be enough examples right here. And so in this particular lesson here, in this particular lecture that I am doing, so allow me to introduce quite a few examples, but then outside of this lesson, I will also post further additional examples where the problem might become more challenging. It might take more time into solving a partial fraction decomposition. Okay, but those are just additional problem outside of this. So if any viewers after learning this video has already feel that you already mastered through with that skill of the partial fraction decomposition and be able to do things on your own, then you don't have to worry about finding my other additional example videos. But if you feel like you want to see more examples, then you can start looking for my other video examples. Okay, so let's now look at example 1. And so right here in this example 1, we are entirely working at just the algebra. We're going to learn. We're going to put ourselves in different various situations about how we can find the partial fractions. Okay, so just like that, in a quite direct instruction here of the problem, we're going to find the partial fractions. Okay, partial fractions of, okay, so partial fractions, there will always be more than one. All right, so allow me to call that part A. So now we're having a starting rational expression as following: x squared plus 2x minus 1. Okay, and that's over one common denominator. One denominator, one big denominator. 2x cubed plus 3x squared minus 2x. Okay, and so that's our, here we go, that's our starting big expression, right? That's our starting big expression, being a one big rational function. And see, denominator and polynomial, denominator and numerator here are clearly two different polynomials. Okay, and the one in the denominator here is pretty high power, degree 3. Okay, and so now let's get to it. So now the real starting step right here, highly recommended, is to be able to factor out the denominator, because that helps you decide how your partial fractions will look like, how each of your partial fractions will look like, okay, or what each of your partial fractions will look like. And so let's spend some time factoring this. Now I leave that for you to be able to factor this on your own. Any one of these, even though it's calculus, but it won't, unless you are preparing for like a Putnam exam or something like that, then you're talking about a crazy challenging. But believe me, any of these polynomials are within your reach. I'm talking to viewers or students of mine who are attempting to find the factors of this. So believe in yourself. You know how to factor this. Okay, so allow me to skip that. You can go ahead and pause the video and spend your own time factoring this. But the final factoring product of this, Okay, the final factor product of this is, so in factor form, 2x cubed plus 3x squared minus 2x. In factor form, it is going to be x times a 2x minus 1 times a x plus 2. Okay, so this is the factor product of all of this, of that entire denominator. Okay, and so now in the way how I see it now, in this factor product, I see 3, 1 of them, 2 of them, 3. That's what I meant by 3. So 3 distinct linear factors. I have this is a linear factor, 1x plus 2. This is another linear factor, 2 times x minus 1. This is another linear factor, 1 times x plus 0. Okay, 3 distinct linear factors. Okay, and really, if anyone feel shocked how I got this, either you can pause the video and grab a quick algebra textbook and learn for yourself, or if you are a student of mine directly in my class, and you can find a way to get a hold of me for extra clarification of how these algebra worked out like that. Okay, but algebra is always highly recommended in any of these work here. So now, once we have noticed that our denominator here can be factored into 3 distinct linear factors like this, then here's the setup, the starting setup for us. I want ultimately at the end, I want my partial fractions to look as following. I need one coefficient to be on top of the x factor. And so for that reason, you have your freedom to name it. Well, I tend to name that a, but you can name it whatever. Okay, but I need a coefficient on top of my first factor in the product. Okay, and then there's another product, there's another factor in this product, the 2x minus 1. So that means I need another coefficient on top of that, 2x minus 1 of mine. And then there's the x minus 2. And so there's an x minus 2, plus 2. I need a third coefficient on top of that. So a is just what I call that to be the coefficient on top of x. B is that whatever coefficient, now we will be leading our way to find these. But B will be on top of the 2x minus 1. And C will be the third coefficient to be on top of x plus 2. And just for these are all being added together. Okay, so that's how it is. So that's the first step right there. And now this can be removed. All right. And so now stay as close as possible to the problem that I have explained on the board earlier. So once we have set out for ourselves a goal here that, hey, we want this fraction, we want this rational expression to equal the 3 partial fractions like this, where a, b, and c are currently unknown right now, then think about the next step. So now if we had these 3 partial fractions, what would happen? How would the process be if we would add these 3 together, and bring those all into one fraction? Okay, so in that way, common denominator is the process, right? And of course, the common denominator is the product of these 3 distinct linear factors. And so that's making it easy a little bit. And so really, a over x plus b over 2 x minus 1 plus c over x plus 2. If we really are adding these 3, then we're going to produce the following. Yes, x times 2x minus 1 times x plus 2 will be our common denominator, our least common denominator. Okay? Because making common denominator is the way how we add or subtract fractions. Okay? And then so now the a coefficient here, which was already on top of x, so now a needs to be multiplied with the remaining other factors in the whole LCD here. And so now 2x minus 1 must be multiplied to a, and then x plus 2 must be multiplied to a. Okay? And then I am going to add. So my b now, so you're starting to click into that pattern right here. B has to be multiplied with the other factors. So b needs to be multiplied with x and multiplied with x plus 2. Okay, and then I'm going to add with c, and c needs to be multiplied with x and the 2x minus 1. My board is running a little short, narrow in space right here, so this is x minus 1 in parentheses. Okay. All right, and so now in the next step, allow me to move to the other board right there. All right, so in the next step, I can see that. So now allow me to write it down one more time right here. This a times x plus 2 times 2x minus 1 plus b times the x plus 2 and plus the c times x times the 2x minus 1. And all of that is over the x times 2x minus 1 times x plus 2. So now one by one we are, see there's the first factor right here with the a term. Well, let's multiply it out. Okay, so multiplying it out, I'm looking at a, and to multiply with, so just FOIL. Okay, so take your time to FOIL. So this is going to be a 2x squared minus plus 3x, okay, and minus 2. Okay, and then plus, now here we're looking at b, I'm multiplying the x into each term here. So that leaves me x squared plus 2x here. And then the last term, after distributing out the x into each term, that I'm looking at plus c, and now 2x squared minus x. All right, and of course it's all over that x times 2x minus 1 times x plus 2. All right, and maybe I'm asking for 1 minute to double check with my calculation on the first one here. All right, and so now in the next step, I am going to multiply a to each of these 3 terms like that, or distribute, and then the same thing with the b, okay, and the same thing with the c right here. And so now this is what I'm getting: 2a x squared plus 3a x minus 2a. All right, and let me double check again. Now plus, and then here we're looking at b x squared plus 2bx, and then the last term here, the last group right here, after distributing out c, it's going to be 2cx squared minus cx. Okay, minus cx, and of course over x and 2x minus 1 over x plus 2. So it's completely all algebra right there. Okay, and so now we can start recognizing like term or combining the like terms. X squared, and x squared terms. Okay. So now we can combine, and so allow me to start moving, being a little skippy here, but now I'm going to combine them and also pull out the common factor x squared there. So I'm looking at 2a plus b plus 2c. This is to multiply with the x squared. So that's my x squared term. Okay, and then I'm looking at the x term. These are my x term: 3a, 2b, and minus c right here. So I'm looking at plus, okay, in parentheses 3a, okay, plus 2b minus c, okay, and then all that there is times x, and that's my x term. And then the last one of mine, minus 2a, and that's all for that. So minus 2a for that, and that was the non-x term, the constant term. And all of that there is going to be over all of the entire LCD x times the 2x minus 1 times x plus 2. Okay, and that's how it happens. All right, so now we have had our rational expressions, and the numerator was successfully put into a polynomial. So this time the polynomial on top is a polynomial of degree 2, x squared term right here. And the coefficient on the x squared term is all this expression, a plus b, okay, and plus 2c. And then the x term is 3a plus 2b minus c. And let me double check right there. Okay, 2b and minus c. And then the last one here is a minus 2a as a constant term. All right, so allow me to swing back to the other board right there. All right, and so now I'm looking at, and so what we want here. And so for this first example, allow me to go with the real close step-by-step right here. I want all of this, 2a plus b plus 2c in parentheses x squared plus the 3a plus 2b minus c x minus 2a. Okay, I want all that over the x times 2x minus 1 times x plus 2 right here. I want all of that there is to equal my starting function right here, because that's what it is. That's what it is. So I want all of that to equal x squared plus 2x minus 1 all over the whole denominator there. So 2x squared, x cubed plus 3x squared minus 2x. And of course, needless to say, I already pointed out so many times in this video already that these two are exactly the same, the two denominators here. And that's why what it leads to next, in order to achieve what we want, the two fractions here to equal, it leads to the next important step. That all right, so here we lead to the next step. Now we can claim that 2a plus b plus 2c, okay, would be x squared plus the 3a plus 2b. And when you are fluent enough, some of these steps can be skipped right there. Minus 2a, all of that must equal the x squared plus 2x minus 1. Okay, so it's all from that we are desiring that this rational expression, this ugly looking one, to equal this version x squared plus 2x minus 1 all over that. And we already recognize that the two denominators are equal. So it led to these two polynomials must equal. And so the way how I see it, these two polynomials, they are both what? They are both degrees 2. Okay, and doesn't matter what degrees they are, but the only way for these two coefficients, the only way for the two polynomials to equal, and the two polynomials are already in terms of the x, of the same variable, then the only way for the two polynomials to equal is that their coefficients correspondingly must equal. And what do I mean by their coefficients correspondingly? You have seen that earlier in the motivation problem, in the motivating problem here, and I'm repeating that again. Meaning this 2a plus b plus 2c is corresponding to the one coefficient in front of the x squared. And then this 3a plus 2b minus c must be corresponding to the 2x, because these are the x terms. Okay, and so in that way, now I can equate. I can start setting up the following system of equation. So my system of equations, of linear equations, just like how you have seen that in the general discussion earlier. Then 2a plus b plus 2c, okay, all that there must equal 1, must be equated with 1. So we produced one equation, one linear equation of 3 unknowns. Okay, and then the 3a plus 2b minus c right here must be equated with that corresponding coefficient on the x term. And so here I'm looking at 3a, and you can see that I purposely line up these variable names right here into columns so that later on, if anyone decides to use matrices, you will have a clear way how to enter your matrix. Okay? So plus 2b minus c, and that equals 2. All right, and the last one here is just simply a minus 2a equals negative 1. So minus 2a, there's no b, there's no c. It means 0b and 0c here. Okay, and all that there is equals negative 1. All right, so now when we're in a formal example, then allow me to skip all of the different way, because again, some viewers, some students of mine can go with the substitution method to solve this system of linear equations. Some other viewers can go with the elimination method. Some viewers can go with the calculator, and some students can go with this, solving this equation as a system of equation, as a matrix. Okay, and so if this is a matrix, then I can help you write down the next matrix, but once I get that, I'll just get straight into the answer, and I'm leaving the method of how to solve this for you to choose on your own favorite choice right there. Okay, but the matrix we produce here, the augmented matrix here is, see, 2, 1, 2, with a vertical line right here, 1. So 2, 1, 2, 1. Okay, and then the next one here is 3, 1, minus 1, and 2. 3, 2, negative 1, and 2. 3, 2, negative 1, and 2. And then the last one here is negative 2, 0, and 0, and negative 1. Minus 2, 0, 0, and negative 1. This is the augmented matrix for anyone who's about to attempt using the matrix method. Okay, so you can go ahead and pause the video and get your work done. Either you can use a matrix here by enjoying your own calculator feature, or you can go with the traditional elimination method or substitution method. I am going to step away for a few minutes to get my own answer as well, and then we're going to compare. All right, and now I would like to share this little information with anyone who is using the calculator. Now, in case your calculator after row reducing your augmented matrix and gives you a decimal answer like the one I'm having right here right now. Okay. So in case you have a matrix that answers are all decimals like this, you have a way to turn these with your calculator, supposedly a TI 83 or 84 calculator. You have a way to turn these back into fractions to re-express these answers in fraction. So, and you can see that A is 0.5, B is 0.2, and C is negative 0.1. But we're going to go math. And then you see right under that math submenu, option number 1 right here, fraction. That I'm going to select that. That means whatever the current answer we've had here, I'm going to turn all that into a fraction. So surprisingly, your calculator is strong enough to take the whole matrix here as an answer and turn every entry in there from a decimal into a fraction. So look at how the magic is going to happen here. All right, and so now we've had our final answer. Okay, and so now that I have solved, and so my A value here is a positive 1/2. My B value is 1/5, and my C value is negative 1/10. Okay. All right, and so now we are ready for to get back to our problem and make the following conclusion. So now I can say that x squared plus 2x minus 1 over 2x cubed plus 3x squared minus 2x. That's here, after partial fraction decomposition, gives us the following. We're looking at 1/2 over, well, just write it in the way of how it is like that. 1/2 is for A, substitute it for A, over x, okay? And then the B value was a 1/5, so here it's gonna plus 1/5, 1 over 5, and over the 2x minus 1. Okay, and then the c value here is a negative 1/10, so plus a negative 1/10. Okay, and then we will do the next algebra, little algebra, over x plus 2. Okay, so all of this here really means algebraically, and like I said, if you are my students who are studying directly with me, you can always get a hold of me some point, right, through office hours or all that to clarify how I move on with any of these algebra steps. But 1/2 over x is the same as 1 over 2x. Okay, and then 1/5, but over x, 2x minus 1, all of that, and positive 1/5, so it's still a plus sign between the two terms here. So 1 over 5 times of the 2x minus 1, so it's 10x minus 5. Okay, because the 5 here is going to multiply with each term there. And then I wrote that a little too close to the other line. Okay, so 1 over 10x minus 5, and then the last one here negative, so negative term right here is going to make that negative, so subtract 1 over, okay, so now 10x plus 20. Okay, but so this is, ladies and gentlemen, this is the partial, these are all the partial fractions of our beginning rational expression. Okay. All right, and so we're now at part B of our example 1 here, and let's continue doing some more partial fraction decomposition. Okay, and so here it's the exact same instruction of the example for any of the problem that I'm putting on the board here. I want let's go through and find the partial fractions of our expression here. So the rational expression we're having here for part B is as following. So for x over x cubed minus x squared, okay, minus x plus 1. All right, so let's go ahead and find the partial fractions of something like this. And so just like how you have seen that through, you know, the motivation problem, the introductory problem I brought up, and through part A of the example. So now this is what I see. We need factoring as first. So let's factor out, and so a lot of time you can also use this as, you know, the factoring work can be placed on scratch work. So x cubed minus x squared minus x plus 1 in factor form is going to be x minus 1 all squared times x plus 1. Okay, and so if you're a student who is studying directly with me here in any academic calculus term here, then get a hold of me so that I can clarify. Or you can always grab an algebra textbook and review your algebra skill right here. Algebra is highly recommended in any of these problems. Okay, but now let me talk a little more about this factor product right here. If we're making some connection with part A we have done earlier, then this one here, it actually has 3 factors, but as far as the distinct factors, then we only have 2. So x plus 1 is one distinct factor, and x minus 1 is another distinct factor, but the third factor is actually a repeat of x minus 1. You see, another way of seeing this is x minus 1 times x minus 1 times x plus 1. That's why I said really as a total count we got 3 factors, but only 2 distinct, and one of them is the repeat of the other one. And so generally speaking, this is the case in this part B right here. We ran into the case where after putting our denominator into a factor product, then we recognize some repeated linear factor. These are all still linear factors. X plus 1 is a linear, and then x minus 1 is also a linear, but one. So in other problem there could be even other ones. So there some other problem there could be, you know, 3 distinct factors, and some of those are repeated. Okay, so this one here in our case, x minus 1 is repeated. Okay, so it has a repeat being a 2 here. All right, so in that way, here's how I set up my starting template right here. So I am going to need, so let's start out with the easy one. The easy one, I mean, the non-repeat one. So this is the non-repeat one. Let's pick that one. So the x plus 1. Okay. Once I decompose this into partial fractions, then the numerator over x plus 1 must be a coefficient, a constant a. Okay, so I have to have something over x plus 1, and that distinct one. But since this is the distinct factor, we only need one term for that. We only need one term for that. I repeat, since the x plus 1 was a distinct factor among, and only has repeats, only has multiplicity 1, or it's only one time itself. It's not a repeat. Okay, it doesn't have repeat like this guy. It only has itself one time, and so I only need one term a over x plus 1. And so you're starting to see where I'm going. So now as I'm done with that, I need 1 over the x minus 1. Okay, but see, you might question me, it's power 2. But hold it, before we get to power 2, we have to get power 1. It's just the way our numbers is. In order to get to 2, we have to get to 1. So instead of writing x minus 1 square, I'm going to have to write x minus 1. So on top of x minus 1, I am going to need a coefficient on top of that, a denominator, a numerator on top of that distinct denominator, but first power. And then I'm going to produce the third one, but being x minus 1 square. So now the repeat here is indicating we got a power 2. So we're going to produce two terms, and it's go in a pattern that first power and then the same factor there, but square power, and then so on and so on. And then I need a coefficient, a third coefficient on top of that. All right, so I hope this all makes sense, but then in a way how I see it, really there are, and I said this earlier, there really are 3 factors, okay? 2 distinct, but really are total 3 factors. So that makes us produce a total of 3 separate partial fractions right here, okay? The first one here is only one term, because it makes sense with how the first factor here was only at multiplicity 1, okay? It only appeared as many as one time here. But then the other factor, it appears twice in the whole product here. That's why we have to produce 1 over the singular, okay, degree 1, x minus 1. But then the third one is over the x minus 1, but square. That's the whole idea. So I hope you start drawing out some other conclusion, conclusion. All right, so plus and plus. Okay, so but after that, so the only part that's tricky is here, but now hopefully once you've gotten that, then things will move on a little easier. Now allow me to get on the other board and bring up some other scenarios before we come back and proceed and advance further. So think about your problem could have started with something like this. It could be the x minus 2 and whatever the numerator, but in the denominator it could have been x squared, right, and then x plus 1, and then the x minus 1 to the cube power, for example. Okay, so if we have some scenario like this, like I said, we got quite a few factors here, and the total here is 2 with 1 with 3. That makes 6 total factors. But as far as distinct, there are only 3. There's the x plus 1, and there's the x minus 1. These are the distinct. And then as far as repeats, the x one has repeats, the x minus 1 has repeats, the x plus 1 has no repeats. X plus 1 has only multiplicity 1. It only appears once. This thing appears twice. This thing appears 3 times. Okay? And so if you had a problem like this, if we had a problem like this, then the setup would be like this. Okay? So if we favor the x as the first distinct factor, then yes, x on top of x, I have to have an a. But that's not enough. I have to need another coefficient for the x squared. Okay? And now see x and then x squared, that takes care of all the x squared right there. Then we're going to move on to the next one for the x plus 1. Now x plus 1 appears only one time in its factor product. Then I need just one single term for that. And then this one right here, it has 3 as a multiplicity. So that means I need a d over the x minus 1. I need an e over the x minus 1 square. I need an f over the x minus 1 cube. And that's the whole idea right there. And then yes, we add all of these guys. So in the end, we're supposed to end up with 6, 1, 2, 3, 4, 5, 6 partial fractions. And that's the whole idea right there. Okay, so I hope without without formally writing down a generalization, right? Because a lot of times if I write down too many formulas, it's going to become confusing. So I hope you're going to start drawing out on your own a generalization about how we carry through with these. And it should also be consistent with how we've done it in part A right there. Okay, and now let's get back to the easier problem of ours that we were in the middle of. So now that's how this is, once again, it enforces our understanding about how I got this here set up. Okay, so now in this way. All right, so I am expecting that a over x plus 1 plus with that. Now if we add, and let's start making common denominator and add. Okay, over that b times x minus 1 over x minus 1 plus that c over x minus 1 square. Then, okay, so allow me to start picking up the pace here in this problem, because all the algebra, except for a couple of new things, but the rest of the algebra is exactly the same. And so I don't need to step too far back and keep explaining every little thing right there. So LCD is, of course, x plus 1 times x minus 1 all square. Okay, and then a here need to multiply with x minus 1 all square. The b coefficient needs to be multiplied with another x minus 1 and the x plus 1. And the c term is supposed to be multiplied with just x plus 1. Okay, and again, go ahead and review your algebra if you have to verify on your own why each one of these has to be multiplied as such. Otherwise, if you struggle a little bit with the algebra and being a direct student of mine in any of the calculus quarter, then go ahead and find a way to get a hold of me through a face-to-face meeting. Okay, but so now, after this point, then we are going to distribute out. So now in that next line right here, so I have the next line. I'm going to have to write it really long right here. So I'm going to start foiling out each one of these factor products. So a and multiply with x squared minus 2x plus 1. That's how I foiled out this x minus 1 all squared. Again, you can always see this as x minus 1 times x minus 1. Okay, and then now go ahead and FOIL out this next one here. So b times now foiling out these terms, these two factors will give me just simply x squared minus 1. Okay, and then the last one here is just simply a little distributive law to apply it here, distributing that c to each term here. And or right now maybe we don't need that yet. C times x plus 1. All right, so this is the step where we're ready for the next board right there. So x plus 1 is here times x minus 1 with multiplicity 2. Okay, and so that's how we're adding all these three partial fractions and combine like terms and bring them into one fraction. Okay, and so now I'm going to take some time to erase my writing on the other board, and let's continue further. So now the first term there, now I'm going to distribute. Okay, so I am going to distribute algebraically each of these right there. Okay, and so just like that, feel free to pause the video and take notes right there, but I won't keep jumping back and forth as often. All right, so I'm going to distribute out the a, so that gives me ax squared plus, and actually it's minus 2ax, okay, plus a. My fraction bar is going down a little bit. Plus, now we're looking at bx squared minus b. Okay, by distributing that b factor and plus, now we're looking at cx plus c. And then all of that here is to be over my x plus 1 times x minus 1 all square. Okay, and so more algebra. So now I'm going to combine like terms. So we got x squared, and those are all the x squared. So a plus b is combined together as like terms. So a plus b in parentheses times x squared. So that's my x squared term totally. Okay, and then my x term is this minus 2a with the with the c right there with the cx. So now it's going to be plus, and then we put everything else here, including the signs in parentheses. So minus 2a plus c. You really have to always to constantly watch out for your algebra. I do make algebra errors right on my lecture as well. Okay, and then plus, and the next one here is we got the constant term a minus b plus c. Okay, a minus b plus c as a constant term added to that, and then this all of this here is over x plus 1 times x minus 1 all square. All right. And so again, just like that, then all of this here. Okay, so in the next step, I want all of this. So allow me to write a little bit informally here. So once we get to this, I want all of this here to equal. I want all of that here is to equal the 4x. Okay, over all of that x cubed minus x squared plus. And actually, it should be a minus here as well. Minus x plus 1. All right, so I want everything that I have ended up here to equal. That's what I want. I want all that to equal this beginning fraction, beginning rational expression. And so that ultimately leads us down to, you see, these two denominators, even though in written form they look a little bit different, but they are exactly the same, because this is just the factor product of all of that, x cubed minus x squared minus x plus 1. Okay, so in that way, the only way for the two rational expressions here to be equal, given that they already had equal denominator, then the only way for them to equal is we can now equate. That means the a plus b x squared plus and minus 2a plus c, okay, as the x term plus a minus b plus c, all of that there has to equal 4x. It has to equal 4x. It's a polynomial on the left-hand side, and that polynomial, in order to satisfy this equality that I need here, then this polynomial must be equal to this other polynomial being a simple term 4x. But so wait a minute. So 4x is only matching with this. So what about the x squared term in here? That means, so if you don't see x squared term, that means this right-hand side is a 0 x squared, okay, and then plus 4x. And we don't see a constant term to show a corresponding term with that. This means it's a plus 0. All right. And so now at this point, we are ready to equate the corresponding coefficients left and right of the equation here. So that means now I'm going to produce, so a plus b must equal 0. That's one in our system. Okay. And then, how about, I'm going to leave a little space here, must equal 0. Someone viewing this video may be surprised why I'm leaving so much space there. There's a reason. And then now minus 2a plus c. So minus 2a, okay, and leaving space here plus c to equal, okay, so that here needs to equal 4, because that's the x term, to equal 4. Okay, equal 4. And then the last term, a minus b plus c. So a minus b plus c must equal 0 as the corresponding term on the other side, as far as the coefficient matching. Okay, so equal 0 again. All right, so what have we made for ourselves here? We've come to for ourselves a system of linear equations. Again, 3 equations, 3 unknowns right there. And again, go ahead and pause the video, make your own choice, select your own choice of the favorite method to solve the system for A, B, and C right there. Okay, so the matrix that we should end up, if anyone plan to use a matrix and with your calculator, then the matrix should end up as the following. So, and that's the reason why I kind of left some space right here to purposely line up these columns of variables. So here I'm looking at 1, 1, 0, 0, and then minus 2, 0, 1, 4, and then 1, minus 1, 1, and 0. That's the augmented matrix that you want to use that for your calculator. Okay, so I am again going to step away for my own calculation and to double check with a few errors here before I proceed any further. Okay, and then I might come back with to correct some of my errors here, because there's nothing to guarantee that I can see everything clearly the whole time like that. So I might swing back here to correct a few errors here. But in case I didn't find any other errors, then once you resume the video, then I'm going to just simply give the final solutions for what A value is, what B value is, and what C value is. Okay? All right, so for any student or any viewer who is going to use the calculator, the TI-83 and 84 calculator, then your matrix is going to look just like this on the calculator itself, like that. And here's the final reduced matrix. So admittedly, I did use the calculator for doing this. And so in this way, it means now I need to erase all of this. And of course, I didn't have to, it looks like I didn't have to correct any errors throughout my example here. And so that's a good thing. All right, so in this way, now after solving the system, then I have found that A value equals -1, B value for us here equals 1, +1, and C value equals 2. All right, so now that means putting it all together. 4x over x cubed minus x squared minus x plus 1 equals, so A now is -1, so it means -1 over x plus 1, okay, plus 1 for B over x minus 1. And we need a third term right here, plus 2 over x minus 1 all squared. And this is how we have come to our final partial fractions, that we have found all of the final partial fractions. Okay? And so now at the end of example 1, and you have seen that earlier that in part A as well, that the whole example 1 is all about our fractions at start here. After factoring it down, recall here that it's it was x plus 1 times x minus 1 all squared here. So the whole example 1 was all about all of those fraction where we had the denominator that can be factored into all of the linear factors. So all of the factors in the factor product here are linear factors. And then we got in part B here specifically, I pushed that into the kind of problem where we had some repeated linear factors among the distinct linear factors. So I am going to write down this generalization, but it's going to be as a formula. So if you don't like formula, you are not required to know the formula, okay? Understand how it works, That's what matters more, okay? So I am going to erase some work here on my other board to make space for me to write down the generalization that we can that we drew out after finishing it through example 1, part A, and part B right there. So generally speaking, so part A is also one case among all the general case of example 1 right here. So example 1 generally brings up the kind of problem where we have a polynomial on top, and the denominator here is in the form as following. So how about we have a linear a1x plus b1. So these A and B, so A is the linear coefficient and B is the constant term, right? And then raised to some repeats, power R1. Okay, so that's one distinct linear factor, but in some repeats, in some multiplicity. And then, how about some A2? So I'm talking about a distinct, so A1, A2 are all different, B1, B2 are all different. I mean, ax1b plus b1 is different with any of the other ones. Okay, so a2x plus b2 to some repeated power r2. Okay, and in products, so on and so on. Some a, we might recognize maybe the m distinct linear factors to some rm. Okay, and so the numerator can be just whatever of a polynomial. Okay, and so, and after we are completely through with the lecture, and I'm gonna even mention some more details, some further details about any of these generalizations right here. But as far as now, the way how I see it, so suppose any one of these randomly has some repeats, then the way how we set out our coefficients. So now I'm going to need an a right there. How about a1? Okay, and over a1x plus b1. So always start out for each one of these distinct factors right here. Always start out with first power, and then I'm going to need a different one. So that's why I'm here. It's going to be a2. Okay. Over ax1, I mean a1x plus b1, but square. Okay. Plus a3 over a1x b1 cube and so on. Okay, that's what the dots are for. And then I'm going to need to add, and now we're moving on to the next one here. And so the next one here, I'm going to need maybe a b coefficients. And so the way is, the idea is, how do we know when to end? We end at, how about, I was not clear a little bit earlier. We're going to end at a, that's whatever the number of repeat R1 right there. Okay, so these are all just A1, A2, A3. These are all the different coefficients on top of each of these, consecutively getting higher power right there. So A1x plus B1 to the R1 power. Okay, and that's why I said, I write it down because in case anyone is looking for, but I don't recommend trying to digest all of these. I mean, know what to do to go is the best. Okay, and then now we're moving on to that next distinct one. So B1 over, and it has to be a different class of coefficients, but they're all coefficients here. Okay, and then a2x plus B2, okay, plus B2 over a2x plus B2, but square, plus B3 over a2x plus b2 cube, and so on and so on. Keep repeating that until we reach, some b to the b sub r2 right there, okay, of the a2x plus b2 to the r2 power. And of course, this formula, this generalization doesn't end yet. We need to keep adding more. Okay, so the more factors that we have, the more we have to keep putting in terms here. And the number of all of these partial fractions, is going to be equal to the total number of factors here, of linear factors, all counted together, including all repeats. Okay, so if say, if all of these guys, there are 6 factors totally. I'm talking about counting all the repeats. There's 2 here, there's 1 here, there's 3 there, whatever, so that makes a total of 6, for example. Then there has to be all together here 6 partial fractions. That's what happens here. Okay.